Hello everyone, today we are going to start off with first come, first serve. First come, first serve is one of the CPU scheduling algorithms. The objective of CPU scheduling is to make system keep working. The first come, first serve is simplest policy perform much better for long process than short one. We have a question here, have a look at the table. We have process, burst time, priority and also arrival time. Now let's do the Gantt chart for first come first serve. For the Gantt chart, arrival time is very important. Let's begin with 0. So let's put 0 here. Okay, the process arriving at 0 is P2, which is process 2. Let's put process 2 here. And then the Gantt chart is always based on the burst time, and the burst time for P2 is 8. So put 8 here, and then followed by 0. The next arriving time is 3. The process arriving at 3 is P5, process 5. So put process 5 here, P5. And then the burst time for P5 is 9. But I did not put 9 because there is a calculation for this part. Previous burst time plus current burst time, which is the previous is burst time is 8 and the current burst time is 9. So you will get 17. So I put 17 here. The next arrival time is 7. But here got two processes arriving at same time. Right? To make it different, go with it and I just change the color. Okay. Which process has the less burst time? Yes, it's P6. So put P6 here. And then the burst time for P6 is 10. The previous is 70 and current is 10. So you will get 27. And then followed by next we have P4 is pending, haven't executed. So put P4 here. And then the burst time for P4 is 11. The previous burst time is 27 and the current burst time is 11. You add it and you will get 38. And then followed by the 7, the next arrival time is 11. The process arriving at 11 is P1. So you will put P1 here and the burst time is 9. The previous burst time is 38 and current burst time is 9 and then you will get 47. And then the followed by 11 there is another arrival time which is in 50. The process is P3 for 50, so you will put P3 here. And then the upcoming burst time is previous burst time is 47 and then the current burst time is 3 and you will get 50. And then that's all for the Gantt chart. And now let's do the waiting time for the first come first serve. Okay, for the P1, how to calculate the waiting for P1? So now let's see, you got P1 here. So the P1 start at 38 but its arriving time is 9. So you have to minus with 38 minus 11. No, yeah, sorry, I have to get the burst time. Supposedly you have to put arrival time here. So put 11, so you will get 27. And then P2 start at 0 and then arrival time is 0. So 0 minus 0, you will get 0. For P3, the starting time is 47, but the arrival time is 15. So you have to minus with 47 minus 15, you will get 32. And followed by everything. So you will get this for the waiting time. And then now let's look for the average waiting time. So I have to add everything and also divide with 6. Why 6? Because you have 6 process here, so I have to divide with 6. So total you will get 94 divided with 6, you will get 15.7 millisecond. That's all for first come, first serve. Next is round robin. Round robin is one of the CPU scheduling algorithm. Uses preemption based on a clock, particularly effective in a general purpose time sharing system or transaction processing system. Now let's do the Gantt chart for round robin. Gantt chart will always based on the quantum time of round robin. So we have 5 here, so 0, 5 and 10. And then as I mentioned earlier, arrival time is very important for CPU scheduling algorithm. So now let's check that. 0 until 5 we have 0, 1, 2, 3, 4, 5. So now let's check it. 0. The process arriving at 0 is P2. So we put P2 here. And its burst time is 8. Next is 1. Is there any arrival time at 1? No. 2? No. 3? Yes. The process arriving at 3 is P5. So put P5 here. And the burst time is 9. Okay. So now let's execute the process. Because there is a no arrival time at 5 and 4. So we can straight away execute process P2. Now minus with 5. Why we minus with 5? Because the quantum time is 5. So we have to minus with 5. So we will get 3. So you put P2 here as you already executed P2. You already executed P2, right? To avoid confuse, you cut it. And we also finish until 0 until 5, so we cut it. And then next is 5, 6 until 10. 6, 7, 8, 9, and also 10. Okay, is there any arrival time at 6? No. 7? Yes. But two process at same arrival time, which is P4 and P6. Okay, we have an instruction for round robin. If the arrival time is same, we can see for the burst time. So let's see here, 10 and 11. Which one is the smallest? Yes, obviously 10, right? So P6. So we already execute P2, right? Queue back the P2 here. The balance burst time is 3. And then as I tell you, P6 and its burst time is 10. And also P4, right? Oh no, P4, right? Yeah. And then you put P4. The burst time is 11. Okay. Now we already execute. We already queue back the process 5 until 10. And then now let's execute the P5 Now minus with minus 5, you will get 4. So as I mentioned earlier, cut it to avoid confuse, and then cube back the P5 here. The balance is 4. Okay, next we already execute P5, right? So put P5 here, and then 10, right? 10 until 15 supposedly. So you put 11, 11, 12, 13, 14 and 15. 15, right? Is the arrival time at 11? Yes, P1. Bus time is 9. And then 12, no. 13, no. 14, no. And then 15, yes. Quebec 15 is P3. So Quebec P3. And you will get P3 is 3. So put 3. Okay, now execute the P2. But P2 is less than the quantum time. So what you're gonna do? So no problem at all. You add 2 plus with these 3. So the P2 is here, and then the arrival time will be 13. So P2 is, you already execute, so just cut it. And then P6, you put it P6, you minus with 5, you will get, what you will get? 5, right? So cut it and cube back it here, P6, which is equal to 5, and then 11, P4, delete it, P4, minus with 5 again, which is, you will get 6, and then cut it, this one, P4, cube back it here, P4, and the balance is 6, and then 5, P5, and now P5. But P5 is less than quantum time, right? The same formula goes for P5, as I mentioned earlier to the P2, right? So you just put P5 and add with the 4 here, so you will get 27. So the execution for P5 is done, and P5 is no more. And then P1 minus with 5, you will get 4. So cut it the P1 and put P1 here, and then cube back P1, and the balance is 4, and the same problem goes here. P3, 3 is less than the quantum time, so as mentioned earlier, so you just put and plus with the 3. Now the execution for P3 is done, so no more P3, and then P6, it's accurate for the quantum time, so P6 also done, no more P6, put your P6, and then P4, 5 6 minus 5, you will get 1, put P4 here, and cut the P4 to avoid the confusion. Queue back the P4 and time is 1, balance is 1, and then P1 again. The burst time is less than quantum time, so as usual, so delete it, put it P1, and then calculate the P4, P1, that is a 4, no more P1, and then P4 less than 1, so put your P4 and P4 also, done execution. And now we already done for the Gantt chart, and next go for the waiting time. So now P1. So the first P1 starting time is 27, but the arrival time is 11, so you have to minus with the arrival time. And then you not only have one P1, you also have another P1 here, which is starting at 45, and the P1 is end at 32. So you have to minus 45 with 32. So you have to add these both to get the waiting time. Same goes to P2, P3, P4, P5 and P6. And then to find the average waiting time, you have to add all of this waiting time. And also you have to divide with 6. Why 6? Because we have 6 processes here. And 116 is the total time of waiting time. And 6 divide and you will get 18.5 millisecond as the average waiting time. That for round robin. Thank you for watching. Thank you.